Good morning everybody and welcome again to our course on Introduction to Mechanical Micromachining. In the last class we have seen some of the differences between the micromachining and micromachining in terms of if you are machining a alloy material or if you are want to machine a anisotropic material. So, we have seen that there are different type of mechanism by which material is being removed in macromachining and the micromachining, and then we started a new topic in that how the specific energy is different in macromachining or the conventional machining and the micromachining. So, let us continue that topic on specific cutting energy. Right. So, that we have seen here that this is a single point cutting tool and this cutting tool is moving in right to left direction, and this is the uncut chip thickness, this is the cutting velocity, this is the width of the chip, and this is the force Fc which is required to penetrate this tool into the workpiece material. Right. So, how you can define the specific cutting energy? The energy consumed in removing a unit volume of material. So, that is called specific cutting energy, and in orthogonal case this is the equation by which we can actually define or we can give a equation that is Fc into V. So, that will give you the energy requirement, and this is the B is the width, Hc is the uncut chip thickness, and V is the velocity, cutting velocity. So, here you will get a millimeter cube by minute or second, whatever you are getting. Then this VV will go away, and then your equation is shortened to the Fc divided by B into Hc. So, this is the shorter version of your equation for specific cutting energy. Now, what is important here, that when your Hc increases, now we will just let us discuss about these two parameter and our force requirement. Now, you consider that we have two situation. So, this is the cutting tool and this is your Hc. This is the one situation, and let us give one more situation on the same graph, that your Hc is bigger now. So, this is your new Hc. Correct. So, now what is understanding of this thing, that if you reduce your Hc, your force requirement is reduced, because now you do not need to remove more material. As the thickness of this uncut chip thickness increases, that is Hc, then you have to apply more forces. So, this is very general idea, and there is no need to apply any theory here. So, this is how it should work. So, smaller the Hc, smaller is the Fc force, that is in normal machining operation, wherever we do conventional drilling machine, milling operation, lathe or turning operation or the drilling operation. Now, what is the problem here? So, this is what is happening. So, this is the same equation here, and we have given the same thing here. The cutting force Fc does not tend to continue to decrease as the uncut chip thickness Hc reduces. Now, what is the problem here? Now, if you see up to this thing, correct. Now, this both the things, this is moving Fc. So, if you reduce your Hc, then your cutting force was continuously reducing, and this was the specific cutting energy. Now, if you see this equation, Hc is in the denominator and Fc is in the numerator, and if you continue this thing, if you see this particular line, this is your cutting specific cutting energy is constant, it is not changing, it is not higher, not lower also, because these both the things are moving simultaneously. If you are reducing Hc, if you are reducing Hc, your force is also reduces. So, both the things are balanced with each other. So, that is why your u is not changing with respect to changing in the specific uncut chip thickness up to a certain level. But now if you see that once it crosses one particular limit, now what happens that this balance is not maintained now. Now this is the yellow pink color line now. So, by particular this trend that if your HC is reducing, HC should FC also reduce, then it should follow this dash line. Then again your specific cutting energy will be a straight line, but that is not the case here, because now here what is the problem, that it is not happening like that, and that is creating a problem in the specific cutting energy. Now you can see that now your force FC is on the higher side. Basically it should lower side to balance this equation, but that is not happening in the micro cutting. So, that is the problem. So, now what is happening? Now let us write that equation again here, u equal to FC divided by BHC, correct. So, now mostly we know that this is in a 1 micron size. So, let us consider 100 micron, and force is also in a 1 to 2 Newton of depending on the material and your other process parameter settings. So, now consider this is in micron and this is in denominator. So, when it will go on the upside, at that time it will be very high. So, if you consider this thing in a meter scale, then it will be the 10 raised to minus 6, and when it will go in the upper side, that will become 10 raised to 6, correct. So, that is what is going to happen in the micro scale, because when you reduce this to a very small level, this thing will reduce. Now, we know that this balance is now reduces. So, now your FC is actually increases, correct. So, that is what is happening once you cross a one particular limit of reduction of the uncut chip thickness, and your HC also reduces, but HC is in denominator. So, now if you consider this is going from 100 to 10 micron. So, basically it is 10 into 10 raised to minus 6 meter, correct. So, now u will be FC into 10 raised to 6 divided by B into 10, correct. So, this become positive, and we know that we are reducing this continuously, which is in denominator, but your FC is not reducing, it is going high and high because of this particular thing. So, now ultimately your u will be extremely high, and that is why now you can see the trend of this u, it is very sharp when it is moving in the this particular region. So, now this particular trend you can understand that how it is being. So, now what we are talking about uncut chip thickness in this particular range. So, now we can think about the specific cutting energy of the grinding, because when you do grinding operation, your chip thickness is very small compared to your turning operation and the milling operation. So, now this increase of this uncut chip specific cutting energy is actually directly connected with the uncut chip thickness reduction with respect to reduction in the cutting force, and that is what is happening here. Now, FC levels of below a certain range of HC, that is what is happening here, and FC needed to cut was larger than the anticipated at the lower HC value. So, we are following this particular line, but this line is not followed when you do machining at a micro scale, and FC does not decrease proportionally to HC causes u to increase dramatically. So, because now we know that our denominator is in micron. So, it will be extremely high when we multiply this thing with the very high amount of forces comparatively here in this case. So, your u will be definitely higher side in the micro machining, right. So, what other way we can define those particular things, that whenever we see the cutting tool, our cutting tool we consider something like this, right. So, we consider that our cutting edge is very sharp here in this particular case, and it is penetrating very perfectly and smoothly into the material. So, you can easily get a chip out of it, correct. But now we know that cutting tool are never perfectly sharp. So, this is a schematic diagram, but whatever way you can see this particular thing at a microscopic level, you always get a rounding edge, and that again you have to scale with respect to the uncut chip thing, how much material you want to remove, and cutting is never a ideal straight line. Now, if you see, this is the sharp tool and this is the actual tool. Now, if you consider, this is the thing, because now our uncut chip thickness is at micro level. So, we have to look our cutting tool also at the same magnification or the same scale. So, this is what is the actual condition of your cutting tool, correct. So, this is considered as a blunt tool. Now, it depends on this blunt tool that how much it will penetrate into the material and how it will remove the material in form of chip. So, when HC becomes comparable to the cutting edge radius, now consider this is our cutting edge radius, right. So, this is the cutting edge radius RC, and now you consider your chip is also here. So, this is your HC, correct. So, now both the things you consider almost same. So, at that time force and energy trends changes. So, in this particular case, that is what is happening. So, you are not talking about the what is the sharpness of the cutting tool when you cut in the macro scale or conventional machining, but this sharpness again play important role when we do same cutting at the micro scale. So, now this is the again trend there. So, this is the HC now, and this is the U in this direction, and this is the range of R. Now, if you consider that this is up to which range, that your U was continuously maintaining its range without any change, but as soon as it is moving in this particular range where the HC is matching with this thing. So, whatever is this HC, so this is equal to R now at this particular value, and now once you cross that value, that means R is now going down and down, and then you are getting a dramatically increased specific cutting energy. So, that is how we can understand this thing. Now, let us see this particular diagram where a uncut chip thickness is given at the x axis. So, this is the chip thickness, and here the resisting shear stress is given. So, now how this thing happens? So, now if you consider your chip thickness in 500s of microns. So, what we do generally, that those type of things are in the tensile testing, that we prepare a tensile test specimen and then you do biaxial testing, and then you can understand that how it is failure occurs. So, if you go in the downside, that if you reduce your uncut chip thickness or the chip thickness, then next operation comes, those things are the turning operation, milling operation, where our chip thickness considering about the 50 micron or the 100 micron or something like that. So, now this is the range. So, now this is the resisting shear stress, that means how much the material will resist when you cut a material with a particular uncut chip thickness or the chip thickness. So, now here if you go down and down in the lower side, then this is called the precision milling operation, that is what we are talking. Let us consider it is a micro machining operation where our uncut chip thickness or the chip thickness is 5 to 10 micron. Now, consider, so this is the grain size or the grain of the material which we want to cut. So, now what is going to happen, that if you consider this thing, the crystal grain void range, so this is less than 10 more than 10 microns. So, this is the whatever these cross marks are given. So, those things are the particular void range. So, this is void range, this is the cavity, that means some porosity is also there, and this is the grain boundary. So, when you are cutting a material at this particular stage, at that time what will happen, that material actually try to find out a weak point through which it can cut the material. So, these are the cavity, the crack is the weak point, grain boundary is a weak point, and whatever is the void is there inside the grain, that is also a weak point. But right now we are talking about the 5 to 10 micron here, So, what is happening here, that this 1 micron grain, it will not actually play important role, because it is, that scale is very small compared to the uncut chip thickness. So, what is the primary probably thing, that it will pass through the grain boundary, and if some grain is coming in its way, that means it will cut the grain also. At that time, this particular whatever void and whatever other defects are available inside the grain, that will play important role in propagating the material. So, this is what is showing here in this case. So, now once this part is over, now if you continue in reduction of this thing, now actually you are going into the detail of the grain now. Now, if you see the dislocation range, now you have to find out what is the distance between this particular void range here. So, here if you see this thing, dislocations are this are within the grain. So, now you are talking about 1 micron. So, when you go in this direction, so this is the 1 micron now. So, if you move into this direction here, then there is a chance of removing or the cutting of a material through this dislocation, correct. So, every time your material will your tool or your cutting mechanism will try to find out what are the weak point of the material in the grain boundary, within the grain, and then it will try to propagate through that particular location. Now, further continue that our depth of cut is less than 0.5 micron. Now, what it will go, that it will go within this particular dislocation. Now, this is the dislocation what we are understanding here. So, this is the 1 micron. So, now we have expanded that 1 micron and then we go inside it. So, now you can find out that there are different type of vacancies there are interstitial atom is available. So, there are lattice atoms available, and this point defect range is now in terms of 0.2 to 0.4 nanometer. So, now your material removal mechanism, or through which the material will remove, it will try to find out these defects within the dislocation. So, what is important thing about this diagram, that as your uncut chip thickness reduces, the number of defects whatever you encounter at the higher scale, it may not present at the lower scale. So, now you consider this energy is continuously increasing if you reduce the chip thickness, and now finally you end up with the grinding, and this is the theoretical shear strength which is reaching extremely high value here. So, that is what is happening in our precision milling or precision micro machining, that we are actually working in this particular area, because we are talking about grain, and then we are talking about the what are the defects within the grain, but we are not going in this particular range less than 5 micron or something, because after that many other things may happen. Your precision and the resolution of your machine tool itself will create a lot of problem, and we have another limitation related to the cutting tool geometry, because you cannot scale down a cutting tool beyond a certain limit, because after that the material of the cutting tool also play important, what are the grain size and how you are actually compacting those things and making it more stable. Correct. So, now this is the HC when you are talking about the more than 10 micron. So, grain boundary becomes the origin of the bracket. So, this is the way it should propagate during the material removal. And when you are talking about HC is a 100 of nanometer to 10 micron, then your dislocation becomes the origin, because so here it was the boundary, now it is dislocation, and if you go further down, then point defects whatever is here, vacancy, interstitial atoms, so those are the point defects. So, those things become the origin of the breakage. So, this one diagram give you overall idea about the how much is the resisting shear stress, that means whatever we are talking about the specific cutting energy, that is also related with this particular diagram. So, this is almost superimposed over this particular diagram, and you will not get any different trend in the specific cutting energy. So, this is what is happening, that your number of defects level is reducing if you go down and down into the micro scale. Right. So, what are the different regions? We have seen many of them. So, let us summarize those things, and we have understood this particular diagram when we started the size effect. So, here we have seen that there are 4 different locations through which we can understand the micromechanics much better compared to the conventional machining processes. So, strengthening due to the lack of defects, so that we have seen in the previous diagram or previous slide. that we are not able to find the enough defects at the small scale of the material or the small volume, and because of that material becomes a ideal material and you are not able to penetrate the tool very easily. Strain rate hardening. So, strain rate hardening, that means that at which rate your strain is increasing or decreasing. So, mostly when you are talking about strain, it is mostly connected with the dislocations. So, when in homogeneity and dislocation, those things are there. So, at with respect to time, how much it is increasing those things here. So, that is again one of the reasons for specific cutting energy, because it becomes very hardened in that case and material removal is very difficult. Reduced temperature softening here, because if you consider the macro scale machining, we know the temperature is very high in some cases where the depth of cut is very high and the RPM and feed rate is also very high. But in micro machining, what we know that we are cutting a very small amount of material. So, when you reduce the cutting edge, so small material removed, right, the depth of cut is small, cut is small, and because of that what is happening, the temperature is also less. Temperature is less and then temperature softening is not happening. Softening is less, let us write less. So, what is happening that when you are machining at a macro scale, whatever the temperature is very high in this particular zone. So, some of the temperature will go to the tool, some of the temperature will go to the material, some of the in the chip and some will propagate it ahead of the cutting tool. So, whatever temperature is playing important, it is softening the material. So, whenever this soft material come into contact with the tool, at that time the material removal will be easy compared to the cold material or the without any increase of the temperature. So, that is not happening in this case, because we are not getting a high rise of the temperature in the micro machining. Right. Strain gradient hardening, because strain is not continuous in this particular case, that means it is not uniform throughout the this particular angle. So, this is the shear plane angle. So, if you consider this particular part here, so this is on shear plane, your strain is variable. So, it is very high here, it is very low here in this particular case. So, because of that you are getting a hardening of the material, hardening here, and that is also one of the reason for specific cutting energies. Now, consider this is the example. So, if you are actually pulling a rod, then you will not get a strain gradient. So, strain will be same at every location of the throughout the cross section. But if you bend this thing, then your strain will be very high here, at the center this will be low and again it will be higher at this particular location. So, now bending and this is the tension, correct. So, in tension you will not get that much strain gradient, because it is uniform strain throughout the material, but when you bend it, at that time it is a variable. So, that is same thing happens here, that one location you are getting a very high strain and another location you are getting a low strain within the same specific zone. So, that is also one of the reasons for high specific cutting energy. Right. So, plastic flow around the blunt cutting tools. So, this diagram also we have seen in previous lecture or previous slides. So, here what is happening, that material is deformed ahead of the tool and some material is actually transferring to the sides and some of the material is accumulated on the face of the cutting, rack face of the cutting tool. And because of that, what is happening, that this plastic flow actually creates a lot of amount of forces when you cut the material. So, we know that if forces increases and your uncut chip thickness is continuously decreases, then your specific cutting energy increases depending on that earlier equation. So, we consider our tool is a blunt, because we know that at micro level there is always one cutting edge radius which is playing important role in the cutting operation. And extension of the shear plan into the workpiece. So, now if you consider this particular thing, that this particular shear plan, so this shear plan actually may get extended inside it and because of that reason that now you have to pull out large amount of material when your shear plane angle increases. So, that much amount of energy you have to spend, again the force requirement will be very high, and that is the also one of the reasons for high specific cutting energy. So, these are few reasons, there may be many depending on the materials and defects of the material. If it is a anisotropic material, if it is a homogeneous material, every time you will get a different reasons for increase of the specific cutting energy. Now, coming to one new topic, that is called burr formation, because we know that when you do cutting of any material, you end up with some of the materials which still stick to the surface, and the later stage you have to do something to remove those materials. So, these are the unwanted materials. So, whatever we are talking about, this thing is this part, this is the part, this is the part, because now if you see, this is the channel which is created, but some materials still stick to the surface. So, now what is the burr? So, it is a material plastic deformation produced at workpiece edge. You mostly find at the workpiece edge only. So, these are the top edge. So, this is called top burr. This is the edge at the entrance or the exit. So, at the time you can call it the entrance burr or the exit burr as a result of the machining or the shearing process. So, these are something which we have to avoid or we have to minimize. Mostly avoid is very difficult, because then you have to set a process parameter in such a way that you can reduce the burr formation. So, what are the problems due to burr formation? So, there are the improper part mating. Now, if you consider this particular part and you want to mate this part with the other part with a flat surface, then this particular burr, it will not allow to mate this both the part together, and that is the reason that you are end up with the improper mating of the parts. Then dimensional accuracy, because now we know that we have to measure our dimension from this particular edge, correct. So, this is the actual shape of the thing, but because of the presence of this thing, it is also difficult to measure at micro scale, that from which location we have to start the measurement of this particular thing. Suppose we want to measure the length of this particular channel, then starting point is very confusing here unless you remove this burr very properly. So, dimensional accuracy also creating problem. Then surface finish, because right now what we are looking at, it's from the top surface only, but burrs also create some problem at the surface which we have some functional requirement. So, surface finish decreases with the presence of burr. Increase the cost of the production, because once these burrs are present, then what you have to do, you have to apply one deburring operation. That deburring operations are actually non-productive, that it does not add any value to the component, it is just to remove this burr. So, it increases the production cost, because ultimately your objective is to remove all the burrs from the component. So, increase of production cost is obvious. And accelerated wear of the devices, now you consider the burrs are present here and this particular surface has a one relative motion. Now, consider that suppose you have one workpiece, this is the workpiece and some burrs are located on the top surface, and there is another component which you have a relative motion. So, this is moving in that is reciprocating in this. So, whatever these burrs are present, what it will do, that actually this burrs will be broken and that will become the interface between the two surfaces. So, let us magnify this surface and you will find that this is the top surface and this is the bottom surface, and whatever burrs are removed. So, this will be in between these two surfaces, and this particular burrs will actually increase the further wear of this particle. So, now these are the foreign element, now it is not attached to the any of these surfaces. So, now these burrs are actually again accelerate this particular wear, that means these particular things will be again dimensionally incorrect, and this will also same thing happen in this case. So, it will further increase the wear of the abrasive any component, because now this burrs considers abrasive particle, because there are sharp also sometimes, and that will actually remove material from the components. And last one is the decrease the device performance, because when you consider bearing operation and if you find that there are a small amount of debris is in between the bearing and the races, at that time this will actually give a non-uniform rotation or the non-continuous motion, and that will result in the decrease of the device. You have to replace the bearings. So, this is the starting point of the burr formation. We will continue this topic in the next lecture. and let us understand this burr formation in much better way in the micro machining operation. Thank you very much.